Okay? And again, I will post this later on YouTube. Mostly, what's nice about YouTube is it does closed captions as well. Okay, so wait, let me just make sure everyone's seeing this. Let me share, I'm just gotta share the screen. Application. All right, so let me close that. Oh, no, there we go. Bear with me. Oh, I miss teaching in class. Here we go. Okay. Okay, so everyone see the PowerPoint slides?
Mm-hmm.
Yes.
All right, cool. So now what I'm going to do is I'm actually going to start teaching here. Okay. Let me see, can you? Oh no, they can't see me. All right. Here we go. Okay. All right. So let me get this started. Okay. Okay. All right. So this is the first slide. This is basically going to be sections P1 and P2 I'm going to cover. Okay. And what I'm going to do is I'm going to treat this like a review because most of the stuff you have seen before. Okay. So the first slide, everyone see its notation, right?
Yes.
Okay, good, good. Okay, if you can't see something, say something, okay? So I'm making this full screen, so let me just see, actually. Well, periodically, I'll press escape and check like that. All right, anyway. Here we go. All right. Okay, so in this class, and the book does it, they actually talk about sets, okay? There is a lot of theory behind what a set is, but really for us, it's just going to be a collection of things, okay? I mean, there's a lot more set theory the book does, but for now, it's really just a collection of stuff, okay? And now you could actually denote a set using the curly braces there, as you'll see. I mean, there's actually a lot of different ways to denote a set. For us, it's mostly going to be this, the curly braces, and you're going to separate the elements by commas as well. So that you'll see actually, and you'll see some examples shortly. And let me just say this, that you don't list an element in a set more than once. Okay? There's no repetition, in other words, in a set. Now, generally with sets, there's going to be a lot of elements. There might be too many to list. So what we can do is we can use these dots to indicate that the pattern keeps going and that there's a lot more elements. But usually you list enough elements so that the underlying pattern is easy to see. And here is our first set, actually, the natural numbers. And I'm pointing this out because, for one, it's our first example, right? We have basically the natural numbers for us is the set of positive integers. Some books use 0 as a natural number. Our book does not do that. See, here we go. But you can see here, though, we have the dot, 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 right? So that tells you this underlying pattern keeps on going. So after 4, you would have 5, and then after 5, you would have 6, and so on, okay? So that's the set of natural numbers, okay? Again, 0 is not a natural number here. Okay, good. So now we're going to get to some more notation. Here is the set of integers, okay? Now, this one's a little weird because we have the dots in front and the dots in back. This is what the book does. So I rewrote it this way. It's the same set, meaning it has the same exact elements. But you can see the integers are, you have the positive integers, right? The natural numbers, that is. You throw in 0, then you throw in the negatives. You have -1, -2, and so on. That's really what he's saying here, the author, that is, of our book. I just wrote it a little bit differently. I thought it'd be easier to see what's going on here. So, is everyone with me so far?
Yep. Yes.
Awesome. Okay, good, good, good. Okay, so that's the set of integers. Okay. All right, so we have that. Then we have the rational numbers. Okay. So these are just basically fractions of integers. In other words, you have a fraction. So you have one integer divided by a non-zero one. That's what the rational numbers are, okay? And these are called rational numbers, okay? So that's what these are. Now, the numbers we're going to be working with are not all rational numbers, though. But we also have our irrational numbers, okay? So you probably have seen, for instance, the formula for the area of a circle and the circumference, right? You've seen that. There's that number in there that pi represents. That's actually an irrational number. What I wrote here was just an approximation for it, but the number pi itself, that pi represents is actually irrational. Irrational meaning it's not rational. So you cannot write it as one integer divided by another. You might have seen the number that E represents. I think it comes up when you do what's called continuous compounding, but you'll definitely see it if you go on into calculus. But the number that E represents, I wrote it here, it is actually a famous number. Oh, there's my mouse. It's also an irrational number. And there's lots more irrational numbers. When we look at square roots later on, we'll actually see examples of irrational numbers. So there's rational and there's irrational numbers. Now, essentially, you put those together and you get what's called the set of real numbers. And really, for the most part, that's going to be our playground, so to say. In other words, we're going to be working with the real numbers, which again is the set of all numbers that are rational or irrational, okay? So those are our numbers that we're going to be working with. And now, I may not get to it. It'd be really cool if I could, but there's actually a bigger set of numbers called the set of complex numbers. And those are all the numbers in this form, a plus ib, okay? Where I is, by definition, the square root of -1. And just in case you don't know what a square root is, I mean, we will cover it later. I, by definition, is the number whose square is -1. And they use I guess, for imagination, so to say, because there is no real number that pulls that off. So we might get to these numbers, the complex numbers, we might not, but should be fun if we get to those, we'll see. Okay. All right, so we have that. Let me just see something. Okay, let me just escape this for a second. Just want to see something. Does anyone have any questions so far? Looks like no. Does anyone have any questions so far?
No.
No. Okay, okay. Good, good. Okay. All right. Good. Let me keep going. Oh, here we go. Okay. We did that already. Okay. Now we're moving on to, so again, this is really just review for us. So what I'm going to do now is look at what are called exponents, okay? And you have seen exponents before, right? Basically, for any real number and any positive integer, right? We have a to the n. I'm really just defining what it is. What does it mean to do a raised to the n, right? Well, you're basically going to multiply a by itself n times, right? So we have n copies of a here. And really, just to make this more precise, what happens if n is 1? Well, a to the 1 is just a. And a is any real number you want. Okay, so raising it to the first power, in a sense, doesn't do anything. Okay, so this is just some terminology I'm presenting here. Basically, a to the n, we say, is a to the nth power, or you can call it the nth power of a. I didn't write this down on the slide, but let me just say this, that the a here is called the base, and the n is the exponent. Okay, so the a is the base, the n here is the exponent. Okay. Now, next, we should have some examples. I threw some examples in there. Again, I'm not going to do too many examples in the lecture today, mostly because it's all review. But if you do want to see more examples, you're more than welcome to see me during office hours, okay? Again, let me just remind you, let me just pause the recording for a bit. If I can get to it. Okay, I think I just stopped sharing for a second, but let me just pause the recording.